All right. Hi, everyone. Thank you so much for inviting me, and I wish I could be there in person. So my name is Abigail. I'm a postdoc now at NYU working with Loredana, and I actually collaborated with Julian on a data-driven approach for parameterizing subgrid effects. But today I will be talking about a physics-based approach that I worked on in the end of my PhD. So this is a paper that just came out this month at JPO. So it's called Modifying the Mixed Layer Eddy Parameterization using Frontogenesis to rest by boundary layer turbulence. So if you want more details after this talk, you're welcome to look it up or reach out to me. And this is work that was done, as I mentioned, during my PhD. So in collaboration with my advisor, Baylor Fox-Kemper, as well as Leah Johnson, Luke Van Rokel, Jim McWilliams, Peter Sullivan, Paul Hall, and Jihai Dung. Okay, so before we get into the details of what the parameterization is, how we modified it, and all that, I just wanted to take a moment to talk about the phenomena that we're looking to parameterize. So on the right here, we see a chlorophyll concentration given by satellite imagery. And what this is really highlighting is the submesoscale flows, which are flows that I assume many of you are familiar with. But these are small, relatively small scale on the order of 1 kilometer. Some features tend to be smaller, some tend to be larger. And they play an important role in the biogeochemical cycle, as you can see that the chlorophyll tends to concentrate along these features. But I'm just going to use this primarily to highlight the features we'll be talking about. So here on the bottom left is a filament that you can see in this long streak, elongated streak. Fronts, submesoscale fronts, are going to be a really big part of my talk. So they can be generally described as a sharp interface between two different types of water with different densities. And along these fronts, instabilities tend to form, which are known as the mixed layer eddies or submesoscale eddies that can be shown here. So there are many different properties related to the physical and dynamical evolution of these different features, but I'll be primarily highlighting the ones that are important for implementing in models. So the last real pictures of my talk are going to be of the front. So as I mentioned, this is going to be a major part of how we modified the mixed layer eddy parameterization. So this image here on the top left is taken from the Gulf of Mexico, where the warm and fresh water from the Mississippi River pours into the cold and dense Gulf water, and you get these very sharp fronts that form. Fronts are associated with a long front current that can transport different tracers. So on the top right here, this is oil from the Deep Horizon oil spill in the Gulf that's being transported along a submesoscale front. And I'd like to point out the difference in width between this front on the right and the left. So you can see relative to the scale of the boats, just how much they vary. And the width of the front is really determined by the boundary layer turbulence that is within this upper boundary layer in the ocean. So that's going to be a major link that we need in this modification. And it also determines a lot of the stability properties. So I'll be getting into some of that math soon. There are several different mechanisms that can lead to the strengthening of the front, known as frontogenesis. And in this bottom image here, this is sea ice that's being carried along with these mesoscale eddy structures and squeezing in the submesoscale frontal feature. And if we were to cut through a front, we would see these vertical or tilted vertical isopycnals, which are at the interface between the two densities. And this leads to overturning circulation in the vertical that is also very important, as I mentioned, for the biogeochemical cycle. It brings up nutrients from the ocean interior. There are a lot of fish that also tend to feed along fronts. So it really does play an important role in several different aspects associated with oceanography. But again, for the purposes of modeling, so mesoscale fronts are a feature that we look at in the upper ocean in particular. And the ocean mixed layer, as many of you know, is the uppermost layer in the ocean. It directly interacts with the atmosphere, so it's affected by all the atmospheric forcings such as winds, waves, heating, cooling, precipitation. And due to all this forcing, it leads to a very well mixed and turbulent layer. But how much turbulence and how much mixing is in this layer determines the effective fluxes that get transported between the atmosphere and the ocean interior. So in order for us to really simulate the interactions between the ocean and the atmosphere, there's really a lot of effort in accurately representing these fluxes in the upper ocean. It's actually turning out to be a really big tuning knob in various climate models, and I assume that the case is the same for Nemo. But depending on how we capture these fluxes, it's really going to determine the overall climate sensitivity. However, many of these processes tend to be very small, fast, or complex. So they go unresolved in GCMs, and there's a lot of effort from the community to try to accurately, or as best as we can, represent them. So down here on the left is a kind of a general form of the buoyancy equation as we can imagine it being solved by the GCM. So the bar terms are the resolution of the GCM, and the prime would be any process that falls below that grid scale. So we can think of these as the subgrid fluxes of the buoyancy. So this is the parameterization that we're trying to capture. And depending on the different physical properties, we can represent these subgrid fluxes in different forms. So two major parameterizations that I'd like to point out that are important for my talk today are the boundary layer turbulence fluxes. So these are like the style of KPP and EPBL for those of you who are familiar. And the main role of these parameterizations are to account for mixing in the terms of diffusivity. And these represent the mixing and deepening of the mixed layer or boundary layer. Whereas submesoscales have the important role of restratifying. So they are actually accounting for positive buoyancy fluxes near the ocean surface. And it's this interplay between these two different processes that will set the effective mixed layer depth that, as I mentioned, is a very important parameter in the overall climate impact. And I will just note as a spoiler, not a spoiler, but as a teaser that Juliana and I are collaborating in M-square lines, and we are thinking about data-driven methods for these type of parameterizations right now. But again, back to the more traditional form. This is again an equation of a tracer that's solved by the GCM. So phi would be now a more general tracer. It can also be buoyancy. But just to highlight the differences also in the different parameterizations. So boundary layer turbulent fluxes such as KPP are parameterized in this form of diffusivity and non-local effects, whereas the mesoscale eddy fluxes or mixed layer eddy fluxes get the form of are used as a form of an eddy stream function. So similar to the Jemp-McWilliams parameterization confined to the mixed layer. And the reason I'm highlighting this is because these two different processes, as I mentioned, interact from a physical sense with each other, but in a climate model, they're actually parameterized in quite different ways, whereas the diffusivity acts as the forcing, and the eddy stream function turns into an advection term. And the real main motivation of our work here is to find a way to link these two different parameterizations because we know the physical processes interact. So let's talk a little bit about what the mixed layer eddy parameterization or submesoscale eddy parameterization looks like. So Fox-Kemper et al. In a series of papers from 2008 to 2011 introduced the submesoscale parameterization. So it's meant to account for instabilities that form along a submesoscale front. So as we saw in the picture earlier, we can imagine that this front has is an interface between these waters of two different densities. It has a frontal width scale of general LF that is currently unspecified. And there's available potential energy that's stored in these vertical isopycnals. And the instabilities that form along them, the mixed layer eddies, will release an eddy kinetic energy in the process. And this leads to this positive restratification of positive buoyancy fluxes. So this overturning stream function is essentially representing the effects of these positive fluxes that are formed by the mixed layer eddy. Now, I won't get into too much of the detail of how the original parameterization was formed, but I will just say that this right hand, like this bulk term on the right side, is representing the W prime B prime, the positive vertical fluxes. And then in order to implement in a climate model, there is an additional rescaling factor that gets introduced to account for all the small the small fronts that are found in one single climate model grid. So recall that submesoscales are on the order of about 1 kilometer or smaller. And climate models, as we know, they can be on the order about 1 degree, 100 kilometers. So this rescaling factor accounts for that integrated average over the entire domain. This introduces this frontal width LF, which is accounting for the smallest front that is used for the integration. And the main point I want to make here is that this stream function strongly depends on this frontal width parameter. So depending on how wide or narrow the front is really going to determine the effectiveness of this restratification parameterization. So there's a lot of sensitivity into this one single parameter. And as I mentioned, this parameterization itself is used as there's a lot of sensitivity to it also in climate models. So there's been a lot of effort from the community ever since this paper came out to try to understand really the importance of this parameter and the robustness of it. And originally it was suggested to be used as the deformation radius in the mixed layer. So N is stratification, H is the mixed layer depth, and F is Coriolis. And in some models, such as POP, this was the case. There is also this like minimum value that's get used. In MOM, the GFDL model, for instance, it actually is just a constant. And in NEMO, there was recently a paper by Calvert et al. In 2020 that suggested a modification to this, which uses the combination of the frontal width and the Coriolis parameter and set that together as a constant. And that gives a lot of numerical benefits, which has been a modification as well. But in either case, there's been a lot of literature that suggested that really the frontal width should not necessarily be determined by these external factors, such as the mixed layer depth or stratification, but rather it should be set by the boundary layer turbulence that is already interacting with submesoscales near the ocean surface. So this is the main motivation for our modification, is that we wanted to find a scaling that represents the actual physical process that's occurring between the frontal formation and the boundary layer turbulence near the ocean surface. So we turn to the turbulent thermal wind balance. This is the work that's been recently been developing. There's a lot of papers by Jim McWilliams' group and Peter Sullivan, Jim McWilliams, where they study the turbulent thermal wind balance and understanding how it interacts with frontal formation and how it can lead to sharper fronts. So turbulent thermal wind, for those of you familiar with the kind of the standard thermal wind balance, it's the balance between buoyancy gradient and vertical shear. And then there's an additional viscous term that is supposed to account for like an Ekman type balance. But what this merely says is saying in the submesoscales, where we know we both have this like QG theory that can be related, but also we've got boundary layer turbulence that's interacting. This three-way balance accounts for these different processes that are important at first order. And in a different paper I did earlier on in my PhD, I investigated the effects of turbulence on the formation of the front. And together with wind balance, we came up with these two guiding features that we wanted to capture in our parameterization. So the first is that frontogenesis, so the formation of the front, is made possible by vertical turbulent fluxes, whereas the frontal arrest process, which means where the front halts at a certain width or starts to dissipate and weaken, is made possible by horizontal turbulent fluxes. So in fact, different turbulent flavors affect the frontal dynamics in different ways, and these are the different elements that we wanted to capture in this new scaling. So it turns out that if you follow through the turbulent thermal wind balance, and you insist that all submesoscale and boundary layer turbulence scalings remain consistent with each other, we were able to come up with a new frontal width scaling that now depends on boundary layer turbulence. Now to go LF in this velocity, and W star, which is the turbulent convective velocity, as well as H, which is the boundary layer depth. And Coriolis parameter. So just to recap, this new frontal scaling is a direct result of the turbulent thermal wind balance. So this is the width where the front reaches at, which obeys this three-way balance between thermal wind and the Ekman balance. So great. So we came up with this new scaling. We then went back to the original parameterization. very important to mention that this formulation is inspired by EPBL, which is a new mixing scheme that's been implemented in MOM 6. And the nice thing about this is that this formula is already computed online in the model, so we don't have to add any additional cost by calculating. We can just grab it as is. So we went back to the original parameterization. So remember that stream function. And when we account for our new frontal width scaling, we get this new formula for a stream function, which one of the nicest features of it is that we now have the Coriolis parameter in the numerator rather than the denominator as it was in the previous version. And this means that we don't need this artificial parameter tau, which was meant to avoid singularities near the equator. So this is a nice feature that came out of just purely implementing this new scaling. And I know in NEMO it's slightly different because this whole term is taken as a constant together. So I'd be interested to discuss that. Okay, so we have a new parameterization. It now depends on these boundary layer terms, and as I mentioned, these are already computed already online in other turbulence schemes such as KPP and EPBL. So it does not add any additional cost to the model by just grabbing these and wrapping them into this new parameterization. Okay, so we have a new formula. It was purely derived by theory. So the next really important step that we made is, does this actually make sense? Can we somehow do some sort of sanity checks to see if this is validated by any type of data that we have for models or observations? So one of the first proofs of concept that we did is we looked at a whole set of large eddy simulations that we happen to have on site. So I'll just note that these simulations were not designed specifically to test this parameterization. They were designed for other purposes, but we used these in order to see if our new scaling made sense in this framework. So these different large eddy simulations, they look somewhat like this 3D version. So there is a front that was being imposed by these boundary conditions. And then there are different types of turbulent properties that are being forced at the surface of the front. And the idea was to see whether our suggested frontal width from theory agrees at all with the measured frontal width in these simulations. So in each one of these simulations, there are varying properties of winds, waves, convection, and other types of instabilities. So what this really means is it means varying U star and W star, which results in different boundary layer depth, and we measure the frontal width. So in each one of them, we measured frontal width that's given by the actual simulation, as well as that predicted by our theory. And I will just note that this coefficient out front, CF, was found to be proportional to the Richardson number, turbulent Richardson number, which turned out to be about 1/4. And this was also pleasing because that represents horizontal shear instability in the turbulent literature. So this again agrees with our a notion that we wanted, this to represent the entire frontogenesis and frontal arrest process. Oh, and also we also looked at a whole bunch of other types of LES that were given in a set of papers by Sullivan and Williams, which was they had filaments. So this is like a two-sided front essentially, and also in a whole set of convection and winds and waves. So we had quite a few LES to test our frontal width. And this here is a summary of all these different results. So up here on top is the predicted frontal width that's given by our theorem. And down below is the measured frontal width that we actually measured from the data. And, although this doesn't agree perfectly, but this is a fairly pleasing result considering that these simulations were not designed for this purpose. And if we were to test a whole bunch of other parameters, we would need to vary one parameter at a time, which is quite costly for large eddy simulations. So the next test we performed is we wanted to see how does this agree with data given from observations. So we used the general ocean turbulence model, so known as GOTM, where we examined different ocean regions where submesoscales have been shown to be important, or more exactly, where there have been observational campaigns that have measured submesoscales in those locations. So this includes the Bay of Bengal, the California Current System, and the Porcupine Abyssal Plain in 2 different seasons. And in each one of them, we use the surface conditions that are given from observations in these locations. And we use GOTM to find the boundary layer depth as well at each location. So we were able to find the estimated frontal width in these different observational campaigns. And, generally we find that most of them, the observed ones, are below 1 kilometer, which is, again, on the scale of what's expected for submesoscale. And in these regions as well, we find regions of intense submesoscale activity, which agrees quite nicely. The final proof of concept was we wanted to understand the global distribution of frontal width to see if that also makes sense on a global scale. So we turned to the MIT GCM LLC 4320. So this is a simulation that's a resolution of 1/48th of a degree. And together with GATM at every grid cell, we are able to estimate the boundary layer depth as well as the surface conditions given by the model. And we compared the distribution of the frontal width with the original one presented by Fox-Kemper, which is the deformation radius. So you can see up here, we've got global winter versus global summer of the old frontal width compared with the new. And down below is the zonal mean of the above. So the blue is showing the old frontal width, which is the deformation radius, and the red is the new frontal width given by our theory. And really the most important takeaway from this is that we are able to describe much sharper fronts with this new scaling, especially far from the equator. And I know that in the Calvert-Doll paper, this was also something that they were able to show, but it's from a different motivation. Okay, so then the final aspect is after we've convinced ourselves that the scaling makes sense, we wanted to see what this looks like when we actually implement it in a climate model. So we turned to CSM-POP, and all we did was use the parameters that are already being computed online. So in this version, it's KPP, and we grabbed U star, W star, and H to compute our frontal width. We tested in 2 different types of simulations. So the first is a coupled, where the atmosphere ocean are able to interact freely. And the second is a forced version of the simulation, where the atmospheric forcing is given from observations and the ocean responds accordingly. So okay, so these are the same version of the plots before, where we're just looking at the global distribution of frontal width. So similar to before, we get these much sharper fronts, especially as we get far from the equator. And I will just like to highlight that in this version of CSM-POP, there is a minimum of 5 kilometers that gets set on this frontal width. And that's set as a limiter, but I hope you can see how artificial this really is compared to what we think is happening from a physical perspective. And the fear was that might affect numerical stability, but that's also in Calvert's paper that's been shown to not necessarily be the case. So we completely eliminated the minimum factor. I think we used maybe 1 meter just in case, but we did not have any stability issues with our implementation. Okay, so the main impact on climate sensitivity that we looked at was mixed layer depth. So we compared, this is the global winter mixed layer depth in observations given by Argo, in the couple simulations given by the new parameterization versus the old, and in the forced simulations given by the new versus the old. And the top right panels are a comparison between the mixed layer depth from the new versus control, which is the old version, in all locations. And the main takeaway from this slide is that it's not drastically different. So it didn't break the model, it doesn't look too crazy, and it's still something that relatively resembles observations, which is good. We didn't want to, break the model or anything like that. We tested this, also for winter and also for summer. And we do see that these general patterns on both the couple and the force generally still resemble observations. But there are changes. The changes are more regional, and where the changes are observed are important climatologically, and there are different regions that have different impacts based on the change of the scale. So this plot is showing the difference between the mixed layer depth given by the new parameterization minus the mixed layer depth given by the old parameterization. So this is showing the change. Deeper is given by the darker blue colors, and shallower mixed layer depth is given by the lighter yellow-green. So I will highlight just some of the results. So the most important probably result is that the equatorial mixed layer depth, especially in the Pacific, is found to be showing, and this is found both in summer as well as in winter, even though it's a little harder to see here. But this result is quite significant because there's been a deeper bias in the equator that hasn't been able to be improved even with the traditional boundary layer scheme. So this is probably due to the restratification that's coming in from this modified scale factor. Additionally, we can also see changes in the North Atlantic, near Greenland, as well as especially in winter in the Southern Ocean. And this comes in both the control, in both the forced and coupled simulations. So there's a whole lot of stuff to look at and a whole lot of different processes that we can examine also to try to understand the real impact of this change of scale factor. And this is something that's ongoing. We're currently also implementing this in a MOM, GFDL's model, and we are planning for a more comprehensive study to really understand the impacts on the climate system. I will just note that down here on the left, this is the mean reduced bias between the new parameterization and observations. And we can see that we reduce the bias quite significantly, especially in the winter, by about 10 meters globally on average. This is compared to the control run. So we do see some improvement, and where we see the improvement is going to be important moving forward. So that's something that we're currently looking at. Before I summarize, I wanted to take advantage of this stage where I have the attention of the most talented climate modelers and advertise Climate Match Academy. So this is a 2-week virtual program that we have a group of 60 or 70 volunteers around the world working to create, and it's going to run this summer for the first time. So we're launching it in July 2023. And the idea is we're teaching open source Python-based tools for people to understand the climate system. And we're touching all different elements of climate, starting from paleoclimate and modern climate and into the future, with an emphasis on impact also. And we're trying to use this platform to really enable climate research from all around the world, whether you have the funds to work with HPC systems or not. So we're looking at this opportunity as really sorry, I'm rambling. But if you'd like to get involved, if you'd like to ask more questions or advertise in your institution, I'd really appreciate it. We're looking for TAs and students and mentors moving forward. All right, so now I'll summarize my actual science talk. We've developed a new scaling law for frontal width as a function of turbulent fluxes given by the turbulent thermal wind balance. And the new scaling is found to be consistent with large eddy simulations with varying forcing parameters. GOTM used to calculate parameters drawn from observations, as well as a high resolution MIT GCM in tandem with GOTM for global estimates. And the results from the new parameterization in CS and POP do reveal that there are changes in mixed layer depth biases. And we're now working on a comprehensive study where we'll be testing bias and sensitivity between observations and various different models. So yeah, I'd be happy to take any questions, and that's it. Thank you.
Thank you very much, Abigail. Very nice talk indeed. I guess there are already questions over there. Takaya.
Hi, Abigail. Thanks for the nice talk. If I recall that the old formulation of the mixed layer parameterization, it wasn't able to capture the sub-mesoscale eddy transport of passive tracers, which are important for, let's say, biogeochemical modeling near the surface. But I was wondering if with this new improvement in the, let's say, formulation of the parameterization, do you see changes in the parameterized sub-mesoscale tracer flux with this?
Yes, so this is one of the things that I've started looking at on a global scale. I do expect there to be changes just because we're looking at the interaction with boundary layer turbulence more closely. I will just say that my understanding is that a lot of the issues were also due to the shape function of the submesoscale parameterization, which restricts a lot of the fluxes to the mixed layer alone. And that is something that I didn't touch in this work. So it would be interesting to see, what is really the cause for that limitation. If you have any suggestions, I'd be happy to talk.
Okay, there are questions online.
Yes, with Bob Alberg has a question, I think.
Hey, Abigail, as always, this is fantastic work. I love the fact that you've gotten rid of this kind of dimensional parameter that's kind of this glaring flag that says, there's a lot here we don't understand, and replace it with solid theory. One of the things in your parameterization, you have both capital H and the boundary layer turbulence. And as I understand it, one of it is a mixed layer depth and one is a depth of active turbulence. They're not necessarily the same. Would you care to speak to the role of these two H's and whether you see a way to kind of reconcile the two or make further suggestions to reduce some of the degrees of freedom that we have due to our uncertainty in climate models in future work?
Yeah, I've been thinking about this quite a lot recently, actually. And I think we need to understand where these frontal features are coming from, and if they are coming from a buoyancy gradient that goes all the way down to the mixed layer depth, then that would be constraining. Just the horizontal buoyancy gradient is averaged over the mixed layer depth. So that's where that parameter comes from. And then the boundary layer turbulence depth comes from the relationship of the interaction with the horizontal buoyancy gradient as it's forming. So there probably needs to be more work to be done on what's going on below the boundary layer and within the mixed layer to understand really what type of restratification is going on there in order for us to understand if this is an important enough feature to capture in climate models, or whether the boundary layer depth alone is sufficient. I don't really have a good answer because I don't know what the data looks like, but the way I've been thinking of it is more like a seasonal average, which determines the mixed layer depth. And then the boundary layer depth is something that would change, even on an hourly or daily time scale. So that might be a way to think of it as a bulk effect.
Great, thank you.
Yeah.
Mike?
Yeah, thank you, Abigail, for a very nice talk. Thank you, Abigail, for a very nice talk. And it's really exciting to see this new parameterization. Because as Bob said, it was very unsatisfactory to have this this length scale that was really rather undetermined in the parameterization in the Calvert et al. Paper. I was wondering whether you've looked at some of the net surface heat fluxes and the variability in the net surface heat fluxes, particularly in the eastern equatorial Pacific, and whether this new parameterization has changes those at all. In coupled models, of course.
Yeah, so I haven't looked at in this study. I haven't looked at all at anything besides the mixed layer depth, and I did start all sorts of diagnostics for the coupled, but that's not something I can necessarily report on right now. But I mean, there are changes. There are changes in the mixed layer depth, and I suspect that is closely related to the heat fluxes in this region. So it'd be interesting to explore that for sure.
Yeah, question?
Thank you a lot. Very interesting talk. I would like to ask you about this new frontal width parameterization for the relatively small scales. When we see the comparison with observations, it's clear that it works pretty well for relatively large scales, and then the mismatch for the small scales becomes quite large compared also to the old parameterization of the frontal width. What is the reason for that? Thank you.
So the question, what is the reason for the large differences?
What is the reason why this scheme is working differently for different scales? When you go to the smaller scales, the performance becomes weaker. Why? Thank you.
I'm sorry, I'm not sure I understand the question entirely. I can give a physical motivation.
Oh, yeah. Just go to this. Probably I got something wrong. Can you go to next slide? Next. Here, yes, here exactly. And next slide also. You see when you, previous.
Okay.
So when you see the small scales, your spread for the relatively small scale for the new paradigm is relatively large, even compared to the old paradigm. Why?
I think what this means is that we have more variability because the boundary layer turbulence might have a stronger regional constraint. So before we had this more averaged version of the frontal width, which is determined by stratification and mixed layer depth and frontal width. So that changes is more averaged if you think of it on a seasonal time scale and then a spatial time scale. Whereas boundary layer depth, as we know, can change from grid cell to grid cell. So I assume that the distribution is more sensitive to just what's happening more locally. From a submesoscale perspective, I think it makes more sense that we're more sensitive to what's happening on the smaller scales because those are the scales that are impacted. So that makes sense to me. But I hope this answers the question. I'm still not entirely sure I understood.
Julien?
Is that okay? Or is there a follow-up?
Thanks for the answer. Julien?
Okay, thank you.
Thanks, Abigail. Julien Lussamer speaking. Thanks a lot for this great talk. Since you're now starting investigating how to improve further this sort of parameterization with machine learning, could you maybe give a perspective as to where you see room for improvement in those representation of some mesoscale and boundary layer turbulence closures? Where do you think that there might be room for machine learning to bring something, and what would be the conditions for this to be like physically meaningful from your perspective?
Yeah, thank you for that question. So I'm using the data I'm using is the MIT GCM LLC 4320 data. So that's a 1/48 of a degree. That only goes down to about 1 or 2 kilometers globally. So it's great for simulating maybe a broader impact of submesoscale. So that would capture some of the mesoscale interactions and stuff that go beyond this like single frontal spin down process, which is captured by this physical based parameterization. So that is what I'm looking to capture and what I think is the limitation as well, because I still cannot get down to these smallest frontal scales. And I think we still might need this rescaling factor, at least to the resolution that we're able to resolve in the MIT GCM. So until we're able to have LES on every grid point, I think we're still limited by the fact that we're not able to resolve the smallest scales.
Thanks.
Abigail, perhaps I could ask another question, which just for you to walk us through what the impact of this new parameterization of LF is on the stream function. So I think you were showing that there's 2 orders of magnitude difference in this length scale between the old and the new scheme, particularly at high latitudes. That is, I think is it that the new scheme has a smaller values? Is that right? Now, what impact is that going to have on the stream function? That's in the denominator, isn't it, for the stream function? And so one might expect then to have a really large impact on the parameterization, but the impact seems to be fairly modest. I mean, it's not 2 orders of magnitude. So what's going on there?
Yeah, thank you for that question. So if I were to go back to this stream function, what's really happening is that H is boundary layer turbulence, and in the denominator we've got these boundary layer turbulence parameters, and H boundary layer depth in models is also determined by these same parameters. So I think it's hard to say on a bulk scale to saying it's only it's increasing restratification. Because there is a sensitivity to how H and the boundary layer turbulence parameters interact together. So I don't have any intuition specifically for saying a sharper LF leads to a stronger stream function, because as I mentioned, the Coriolis parameter also gets eliminated. So it's this new formulation as a whole. I think that's more intuitive. So I would say that when we have smaller boundary layer turbulence and a larger maybe forcing, so you would get a certain effect, and the same would be vice versa.
Thank you. Julien again.
Yeah, me again. So this is all very fine for models that actually have either a KPP or in this case an EPBL boundary layer scheme. But what about models like the Nemo ocean model, which is using more of a local turbulent kinetic energy based representation of upper ocean turbulence? So have you put a bit of thought about that? What would be the avenue for adapting your methodology to other boundary layer schemes?
Yes, thank you. So as long as we have these surface conditions, so we have buoyancy fluxes and wind stress, we can recreate these turbulent scales, and that could be used within this formulation. It doesn't. I mean, I in POP I use this formula, but I use these constant values for n star and m star, which are just taken as the average ones from the EPBL scheme. But these parameters could still just be taken from the model as is, which I did for KPP, and inserted in LF. So we could still get the scale factor. But perhaps there's something more clever to do with the way Nemo is computing the boundary layer scheme. I haven't looked too closely on that scheme, to be honest. So I'd be happy to discuss implementation if that's something you're interested in.
Thanks.
Thank you. Alexandre?
Yeah, thanks for the talk. Just, I think, a naive question, but at which resolution do you advise to use this parameterization, and particularly, do you test it at different resolution and even at very high resolution, or is there a risk to add it at high resolution?
I think we would need to just be careful that they're not the submesoscale eddies are not resolved together when the parameterization is on. But that's also one of the things that we're going to be testing in this multi-model experiment, is also test several different resolutions. But if I go back to the parameterization, we've got this scale factor in here that's related to the grid scale. So it will turn on when we need this rescaling factor, which is probably somewhere in the mid latitudes, depending on your resolution, and then you could have this smoother version as you get closer to the equator. So I don't know if there's any risk, but as long as we don't double count, I think that the restratification effects are probably important enough to parameterize.
Thank you. Questions? Takaya?
Hi, sorry again. This is going slightly beyond my expertise, but have you looked at how this new formulation behaves under sea ice?
That goes beyond my expertise as well. I have not, but I have. There are changes close to in the mixed layer depth, close to the poles. So I suspect that is impacting the heat flux near the ice sheets, and I would intuitively say that we should see some sort of impact, but I don't know too much about sea ice coupling with the ocean model in specific modules. Sorry.
I've got a naive question as well, but probably more naive than Takaya's. I was wondering the plots you show with coupled and forced simulations. How long are they? How robust are those maps to these comparisons? I mean, how many years maybe did you use to do that?
Yeah, how many years? I think the forced ones I used the core V2 forced simulations for CSM, and I ran them for 6 cycles, and I think I averaged over the last one. So each cycle is like 55 years or so, or I forget the exact number. I'm sorry, I have it in the paper, but it's maybe 60 or 70 years for each cycle. So I averaged over the last cycle. So that was like a standard test I used. And then the second one, the coupled one, I probably ran for 300 or 350 years and then averaged over the last 100.
Okay, that's pretty solid then.
Yeah.
Okay.
Yeah,
Thank you.
I used a standard, like some sort of standard practice that I forget
Okay. All right.
where it was from. Yeah.
All right. Any other question, either online or on site?
I have a comment,
Yeah.
actually, following up on the high resolution question. So Takaya led a paper recently which compares high resolution submesoscale simulations of different versions. And in that paper, they tested the submesoscale parameterization without this rescaling factor by the assumption that we have sufficient submesoscale activity in these super high resolution simulations, so it's not needed, and or at least they didn't want to get into that, I think, but I think that would be an interesting test bed for this hypothesis of like whether submesoscale are partially resolved or fully resolved, or do we still need some sort of rescaling factor? Would be an interesting thing to test.
So Takaya is nodding here. Would you like to answer?
You can try at least.
Okay.
I agree. It would be really interesting, but I guess it also depends on the outputs saved. I don't think the outputs are saved that are needed to calculate the frontal width, unfortunately, in the formulation that you have. But yeah, I mean,
we can chat because the EM does have them. So I'm actually looking at that now for the LLC 4320 data. So yeah, we can chat and see if there are other parameters that are needed from other simulations.
Yeah, sounds good. Maybe I'll send you an email.
Awesome, thank you.
So we have another question online from Jérôme Chanu. If you can formulate your question, Jérôme, maybe.
Simple question. So now we can consider that the new proxy to have a mixed layer Eddy resolving model. We have to consider the new length scale that you propose, right?
Mm-hmm. Yeah.
I was referring to the Dong et al. Work.
The MLI instability. Yeah. So following up from this.
In the paper, they assume that considering this length scale for mixed layer eddies, you can see where your model is mixed layer eddy resolving or not. So we should replace this length scale by yours to do such a computation.
Well, this is not showing the mixed layer instability, which is what the Dong et al. Paper did. This is showing the smallest frontal width. So whether or not that's the important process to simulate entirely is a question, because the frontal width would be which determines the front, and then the eddies form around it, which then determines the instability. So it's a slightly different process, I think the Dong et al. Paper also argues that even in the MIT GCM, it's not sufficient to resolve MLIs, especially in the higher latitudes, if I remember correctly. So I think this is still telling the same story, but if you wanted to fully resolve submesoscale activity down to the smallest frontal scale, I would suggest to go with the frontal width. But that's a bit crazy, and especially in the high latitudes.
Okay. Well, anyway, we are very far.
And we have.
Yeah, I don't know. I need to think about that a little further.
Apologies. And we have one more question by Bob Alberg online, and I think we will probably then close the question session. Bob, your turn.
Thanks. So in the original parameterization, and here also, we're using large horizontal fluxes, large overturning against the model's weak gradients to get the right restratification, with the result that the overturning stream functions tend to look large if you interpret them naively, looking at, let's say, zonal means. Use the new scaling to kind of scale down those implied overturning stream functions in a way that if people are looking at, say, the contribution of your parameterization to the zonal mean overturning circulation, that we can scale it down so that you're getting answers that are maybe more sensible and that people might be more comfortable comparing with observations.
Yeah. Yeah, I don't have a good answer for that. But I will say that, this coefficient up front will determine a lot of that. So whether or not, the order of magnitude is a quarter or one or larger, will really determine, how strongly you're restratifying and how strong your stream function will be. So I suspect there's quite a lot of sensitivity in that parameter over there, and that could be used, to downscale or upscale this, much like a tuning parameter. And this represents what we think of as the arresting factor. And there have been several studies that have suggested that, that could be symmetric instability, which would require a larger coefficient, or if it's the horizontal shear stability, which is a smaller coefficient. So that type of distribution of what's really going on in the real ocean is something that I don't think we're able to calculate yet. So in the meantime, I would say this would be the coefficient that can be used to look at the strength of the stream function compared to other overturning circulations in the ocean right now, maybe to get a physical sense of it.
Well, or alternately, it's that delta S over the LF is where we get an overturning stream function that looks large, even though physically it's doing the right thing for the restratification. Mm-hmm. That may be a metric worth saving for the interpretation of the stream function, even though what it's doing physically in the model, I think, is very much the right thing. Thank you.
Thank you, Bob. Thank you, Abigail. I think it's time, right, Julien?
Yeah,
it's time to close this very interesting. Oh, you're showing the people.
Yeah, I was just here. Just making sure that you see the crowd at least just a bit. Thanks a lot for this great talk. Thanks for agreeing to give it in a distance. It seems that you've proven that we can have interesting discussions with hybrid events. So that's one step further in the 21st century. We're very happy with this, and thanks a lot for this great talk and great discussion. Unfortunately, you will not be able to chat with us here during the poster session, but for the local attendees, we'll now move gradually to the posters and then have a nice social dinner in the evening. Thanks a lot, Abigail, again.
Yeah, thanks so much, everyone. I wasn't able to see your faces when you asked questions, so I apologize if that was awkward. Thank you for the great discussion, and please reach out if you'd like to discuss further.
Yeah, let's continue on email. Thanks.
Thanks a lot.